Okay, well, it's a very great pleasure to have Jesse Lansdown from the University of Western Australia start off the afternoon session here. And his title is, There Are No Block-Transitive Subspace Designs. Thank you very much, Jesse. Over to you.
Thank you, Stephen. I just want to point out this is joint work with Dan Horton. And yeah, we looked at block-transitive designs and show that none exists. So the title kind of gives away the talk. But before I get into subspace designs, I want to talk about block designs because they're a little bit simpler to understand and sort of more classic as well, sort of been studied for a while. So a block design has parameters t, d, k, and lambda, where we have a set of points of size d, and we take k subsets of these points and we call them blocks. And then the thing that makes it a design is that we have this additional property that if we take any t subset at all, it is contained in exactly lambda blocks. So here's a classic example. You've probably seen this in different settings, the finite plane. It arises in all sorts of situations, such as being the smallest projective plane, but it's also a block design. It's a 2-7-3-1 design. So you can see there's 7 points. If we look at the lines, then there's 3 points on each line. So we have k is 3. And no matter which pair of points you pick, the 2 set that defines will lie on exactly one block. So this point and this point uniquely on this block. So lambda is 1. And in this case, we also call that a Steiner triple system when lambda is 1. Now, subspace designs are essentially the Q analog of block designs. So we take the word set and we replace it with the corresponding vector space definition. So over FQ. So in this case, we no longer have a set of size D, we instead have a vector space of dimension D. And so now we are over the field FQ, so we have this additional parameter Q. And then the rest behaves in the way you'd expect. So we have k-dimensional subspaces forming our blocks instead of sets of size k. Instead of t sets of size t, we have t-dimensional subspaces, but they're still contained in exactly lambda elements of B. Now, so I could give you very quickly and easily a block design, the finite plane. And then so the natural question is, do these things exist in their Q analogs? And certainly when it comes to the finite plane, that's a big open problem. And a lot of people have spent a lot of time trying to answer that question when Q is 2 in particular. But back in 2016, Brown and a few others showed that actually there do exist Q analogs of Steiner systems. But it seems that in general, they're much harder to find and perhaps, yeah, don't have as nice properties in some sense. For example, one of the things we'll often study when we look at block designs is symmetry. And in this case, the talk is focused on block transitivity. So what that means is we take the automorphism group of our design and it's transitive on the blocks. That is, there's a single orbit on the blocks. And for block designs, that's fairly well studied. And in fact, stronger properties are studied, such as 2 transitivity, block transitive, but point-in primitive, flag transitivity, and things like that. And if we add in additional constraints on, say, lambda, we often can classify these things as well according to their symmetries. But the Q analogs are a lot harder. So remember the finite plane, that the Q analog for QX2 is still not known to exist, but what we do know is that if it does exist, it either has no symmetry at all, it has a trivial automorphism group, or it emits a single involution. And even other subspace designs which are known to exist still typically have much less symmetry. So most of the known examples I can think of, their automorphism groups are normalizers of Singer cycles and things like that. which raises the natural question, well, are there block-transitive subspace designs? And the point of this talk is to say, no, there's not. Now, you can see here, we've got some parameters. K obviously has to be less than D because we can't take our subspaces to be the whole vector space. And of course, we want to contain smaller subspaces. That all makes sense. But we do have here that T has to be at least 2. And if you take T to be 1, then there do exist examples of block-transitive subspace designs. And in fact, these things are studied in their own right as K covers and K spreads and things like that. I'm not sure entirely about the transitivity of them, but they do definitely exist. But as soon as you take T to be at least 2, they don't. Now, I've talked about transitivity, and that implies sort of automorphisms. And so I just want to make an aside about how we're thinking about these automorphisms. And we're thinking about them essentially as automorphisms of the Grassmann graph. So the Grassmann graph, you take k-dimensional subspaces and you make them your vertex set, and they're adjacent if they intersect in a k-1 dimensional subspace. And the automorphism group of this graph is then what you would expect it to be most of the time. It's P gamma L. But if your K spaces are exactly half the dimension, then we get this extra C2. And that's, I guess the graph is sort of preserving the subspace lattice structure. And in the case you're half the dimension, you can kind of invert things. And so we take our automorphism group of our design to be inside of the automorphism group of this Grassmann graph. And essentially you can't really get any bigger than this without losing the embedded structure that you would have inside of the vector space. And this C2, that corresponds in this case to if you have a self-dual design, then that duality can act as a sort of automorphism. So what that means when we're considering transitivity is if we're inside of P gamma L, we have a single orbit, but potentially we could have 2 equally sized orbits that get fused together by this duality. Now, there's a lot of parameters to consider to show that these things don't exist. So it's helpful to first simplify some of the parameters. And we can do that firstly by restricting ourselves to K being at most D on 2. And the reason for that is because if we have a block-transitive subspace design and we take the dual, then that also gives us a block-transitive subspace design. So if K is too big for our liking, we simply try and determine whether or not the dual can exist. And then secondly, we can actually constrain ourselves to the case where T equals 2. And the reason for that is because if we take any T design where T is greater than or equal to 2, then it's also a 2 design. And so we have the block set is unchanging. So the automorphism group is unchanging, but we're just kind of, our perspective is changed. We're considering the blocks with respect to two-dimensional subspaces instead. And so of course, that means that the number of things that they're contained in will change. But yeah, so these two together are quite helpful. Now we only have to consider T equals 2 and K we can assume is at most D on 2. And also that means that D must be at least 6 because obviously K has to be at least 3. And then if we're at most half of D, D has to be 6 or greater. And so what we want to do is we want to go and we want to take these subspace designs. And at the moment, all we really have is parameters, right? We don't know much about them other than this. So we need to somehow relate these parameters to possible automorphism groups. And the way we do that is by considering primitive divisors. And so a primitive divisor is just of q to the e minus 1 is just a divisor of q to the e minus 1, but it has to be co-prime to anything that sort of has this sort of format where we have I less than E. Okay, and the largest such prime divisor we call the primitive part and denote by phi star. And just a quick comment about some of a property of prime divisors is that they have to be odd when we take E greater than 1. So if we took Q itself odd, then Q minus 1 would be even. And so since we're co-prime to anything where I is less than E, that would mean that the divisor must be itself odd. And in the case that Q is even, then what we get is that Q to the E minus 1 is clearly itself odd, so any divisors would be odd too. And now here's kind of the crux of our result, is sort of this lemma which connects the prime divisors to the order of G. And here you can see we've put in the simplifications where we're taking T to be 2, and we're saying that K has to be at most D on 2. And then we take G, which is the intersection of the automorphism group with P gamma L. And so essentially what we're saying here is it's the automorphism group inside of P gamma L. That is, it's the setwise stabilizer of the blocks inside P gamma L. And we're not worrying about that potential duality. And in that case, the product of these prime parts divides the order of G. And so I thought this would be a good place to have a sketch of a proof. And we start by counting the number of blocks. And so you can come up with formulas for this, which involve the Gaussian coefficients or the Q binomial coefficients. And since we've only got 2 for T, it means that there will only be 2 terms on the top and the bottom. And then clearly, this prime divisor has to divide this term. And similarly, this divisor has to divide this term by definition. And because these are prime divisors and this is one less than this, we get that these are co-prime to each other. So their product will divide the top. They won't have anything in common there, but also they don't divide any terms on the bottom because D has to be at least 6. And so, and K is at most D on 2. So D minus 1 is less than K, is greater than K. And so by the definition of the prime divisors, each of these are co-prime to these terms. So that's good. And so the next thing to think is, well, okay, G is either the full automorphism group, if it's contained entirely in P gamma L, or we get its index 2. And so either way, what that means is that the number of blocks has to divide 2G because we're block transitive. And so this so that means that then this has to divide 2G, but recall that each of these have to be odd. So we're co-prime to the 2, so we must divide G. So there we go, we've connected the parameters and the prime divisors to the order of a potential automorphism group. And what we then do after that is we can go through this classification. So Bamberg and Pentilla have this classification of subgroups of GL that are divisible by some prime divisor, assuming that that prime divisor is non-trivial. And essentially this gives you a whole bunch of options. I've summarized them here into different types of examples according to the examples in their theorem, but the actual theorem runs over like 3 pages. There's a bunch of families, and then there's numbers of tables with specific groups that can occur. And so at this point, what we need to do next is kind of go through and consider these different groups and see whether they're permitted by the parameters of different designs. So to begin with, we assume that each of these prime divisors are non-trivial so that we can use this theorem. And then essentially we get sort of 2 cases happening. We either get this sort of one-dimensional case which corresponds to the extension field example, or we get everything else. And so to begin with, I'll start with everything else. And I'm just going to fly through these because it's all kind of the same thing, just applying the divisibility conditions. But in the case where we have classical, reducible, imprimitive, symplectic, or nearly simple automorphism groups inside of GL, then we require these prime divisors to divide that group. And we get a whole bunch of families and lots of finite cases which are listed in tables, and we go through and we consider the divisibility conditions of them and see whether that can happen. And so in some cases that's a reasonable amount of work for some of the families. In other cases you can just kind of read them off and see they don't work. So you get things like this table where you have, okay, these are the prime divisors. Here you have values for E and Q. And so for example, we require E to take the values of D and D minus 1. And so you go through the table and see, well, when does that occur? And if it doesn't occur, you can rule them out immediately. If it does occur, then you have to keep doing a few more things and get contradictions that it can't happen. And for most of these cases, that's enough. You can do that. In the one-dimensional case, it can be a little bit more work, but we get a similar thing. So we have this extension field case, and we get the prime divisors have to divide the automorphism group inside of gamma L. But we can't get rid of all the cases by just using divisibility conditions. Instead, we can reduce them down to 3 possible cases. And in the first 2 cases, we can convert those into some other design and say they don't exist. So for example, this one here produces a K cover or a K spread, I can't remember which. And then, or rather implies the existence of one, but it has parameters which are non-feasible. So we can eliminate that. And then this one here we can find in the literature and see that it doesn't have can't have a transitive automorphism group, block-transitive automorphism group. And then the final case we had to eliminate by computer. And in some sense, this was kind of one of the hardest cases, but it was also kind of one of the easiest cases. It was hard because we couldn't kill it with just divisibility conditions, and it was too big to fit in computer memory. It was quite massive. But we were able to, in the end, produce canonical representatives for each of the orbits under the putative group. And then at that point, it becomes easy because then it's just a matter of checking if these orbits on their own form a design with the right parameters. And of course, once we've done the computations, we have everything. It's much easier to verify, which leaves the final case. So remember, to use the theorem of Bamberg and Pentilla, we had to have both of these things to be non-trivial. And of course, if they are trivial, we can't use that classification, but we can reduce it down to 2 cases by Zygmundi's theorem, where we have designs where Q to the D or Q to the D minus 1 is equal to 2 to the 6. And then you can do a bit of work and show that they don't exist. I can't remember all the details, but we start with some divisibility thing and show that that constrains something, and then we consider that that group can't fix a subspace, and then show that that leads to a contradiction. And that basically concludes my talk.
Thank you very much, Jesse. So